Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Amir Excel is here today to discuss his book, Uranium Wars, the scientific rivalry that created the nuclear age. Uranium Wars is a story of science, intrigue, egos clashing, spying, and international conflict. Uranium became, through chance discoveries and a string of intricate decisions, the central character of one of the most important political, military, and scientific developments of the 20th century. From the nuclear programs in the Middle East to plans for nuclear reactors at home, uranium is never far from the headlines. Called one of our best science popularizers by Publishers Weekly, Amir Excel is the author of 14 books, including the international bestseller Fermat's Last Theorem. He's currently a visiting scholar in the history of science and a fellow of the John Simon Guggenheim Memorial Foundation. So please join me in welcoming Amir to Microsoft to discuss Uranium Wars, the scientific rivalry that created the nuclear age.
Thank you very much. It's a pleasure to be here. Can everybody hear me? Is this working? The last time I was here, I spoke in a small room in a small, I think it was a small building, another side of campus. So it's a pleasure to be here. I started writing this book because I was worried about Iran. That was a year ago, and all the news about Iran seemed that nuclear weapons are falling into the hands of all kinds of nations, and God help us if organizations as well. And so it's a year later, and the book is out, and I read the news, and I'm more worried about Iran. So if you're trying to write a book as therapy, it doesn't work. So at any rate, the story, I hope, that I found while researching this because of my fears is a good one. And I found it very interesting to try to understand uranium, what it is about it that made it the most important element really in the 20th, defining the 20th century and following us into the 21st century. In a game whose rules have shifted very much since the end of the Cold War. But I want to start at the beginning. So radiation was discovered in 1895 through the work of Röntgen, of course. This was a chance discovery where he was working with something electronic, a type of an X-ray machine, but the prototype, and he noticed the glow, something I guess like the cover of my book, from on a bench far away, not far, a few feet away, and turned it off, and the glow stopped. So you realized they discovered something. And if you go online, you can see his wife's hand, the inside of his wife's hand. This was the first X-ray ever taken, which I thought was interesting. So people immediately asked themselves the question, is it possible that there are natural elements that emit radiation the way that X-rays were produced artificially? And it took only a year to realize that the answer, in fact, is yes. A French scientist was taking some photographs outside. Remember, the photography was invented in the late 1800s, and these were among the first photographs that were taken. There was a cloudy day, so he kept his plates inside the drawer, and he had some uranium salts next to it. So when he developed it, he realized that they were fogged up, and so radiation was found to be the cause. Marie Curie and Pierre Curie, her husband, did a lot of work, a lot of the early work on radiation. She discovered radium and polonium, which she named after her native country, Poland. And this became a kind of an industry to try and find radioactive elements and understand their behavior. Her daughter, Irene Curie, and her husband, Frederick Joliot, continued the work of the Curies in Paris. And at the same time, the early 30s already, there was another team. This was a team in Paris. There's a team in Rome headed by Enrico Fermi, who made his name on uranium and was part of the Manhattan Project and is really the central character, one of the central characters here. And there's a third group in Berlin, headed by Otto Hahn, who was a chemist, and Lisa Meitner, an Austrian Jewish physicist. This was the early part of the 20th century. It was very difficult for women to get into academia. It just is shocking to find out how strongly women were discouraged to seek any kind of academic training. And it starts in the lower schools where girls were, well, they had no way to get into academic, to get any kind of preparation to go into a university. So the boys went to another kind of school, and the girls were trained to do housework and things like that. So this was a naturally born physicist who had to really work very hard, and even her parents didn't want her to become a physicist. She took a tutor to bring her up to speed with what the boys were learning in school, and she managed to get a doctorate at the University of Vienna, and then she moved to Berlin. When she got to Berlin, there was Max Planck there. Planck, of course, was the first discoverer of the quantum idea. And she came to take his seminar, and he was very kind to her. And then he asked, why do you want to take my class? So it was that kind of, the way, the discouragement of women was complete. Even somebody with a doctorate was, why would you ever take an academic course? You got a doctorate, but stop there. Don't get near academia. But she didn't take no for an answer. And when she started working at the Kaiser Wilhelm Institute in Berlin together with Hahn, she had to work in a basement. She was not allowed in rooms like these upstairs. Well, not as nice as these, but rooms upstairs where the men were doing research. Her lab was a carpenter's bench in the basement of the building. But Lisa Meitner was such a brilliant scientist that apparently she didn't mind taking the discrimination. Eventually, she worked her way up, and she was the most important scientist, along with Fermi, in the research on uranium. So now the work among these three groups was a competition, a very fierce competition among these three different groups in three different cities in Europe, trying to, well, three capitals in Europe, trying to understand what uranium is. So I'm going to stop the history for just a few minutes and try to explain the science. What happens with uranium, by the way, is that mass... My electron is gone. Oh, no. What am I going to do without an electron? This is awful. When you lose an electron, you're in trouble. I think the electron is on the floor. Oh, right. Very good. Yeah. No, it's okay. I'll live without an electron for a little while. So what happens here, it's somewhere here. If not, we'll get it from out of the one of the computers. So mass and energy are related, and I thought you'd enjoy this one.
With mass and energy are both often different manifestations of the same thing, a somewhat unfamiliar conception for the average mind. Furthermore, the equation E is equal mc squared, in which energy is per equal to mass multiplied with the square of the velocity of light, showed that very small amount of mass may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Kopler and Walton in 1932 experimentally.
Do you know who it was? Of course. Yeah, that's one of few recordings of his voice. You can find it online, but it's hard. It doesn't come up on search engines very quickly at all. In fact, if you have to go to the AIP, American Institute of Physics site, and then you'll see it. So of course, mass and energy are equivalent, and that is an incredible principle. We are all energy. In fact, a Nobel Prize physicist who I interviewed a couple of months ago told me that if you weigh 150 pounds, about 3 pounds of that is actual mass. Your quarks, the quarks inside your protons and neutrons, and the rest is the binding energy, which is amazing. So we're much more energy than we are mass. So the quarks are these three little guys that live inside. This is not the electron. The electron is smaller, which is why I can't find it. So inside a neutron or a proton are these three quarks. So these quarks are the mass, but they keep playing ball using the gluons, and they move all the time. So we are really the binding energy and the kinetic energy of these quarks. The two up quarks and the down quark in a proton. I didn't lose all my protons. Here they are. So the protons here are the white ones, and the black ones are the neutrons. And the electrons go around here. So this is a nucleus of an atom, and it has both the protons and the neutrons. Now, so each one of them has these. The two ups and a down makes a proton, and two downs and an up make a neutron. So when you have something called beta radiation or beta decay, a neutron becomes a proton by one of these quarks changing from a down to an up. And this was discovered by Enrico Fermi, beta decay, and in fact Pauli, who was also a quantum physicist, discovered the neutrino by looking at the energy that's released when this beta decay occurs, when a neutron turns into a proton. An electron comes out, but there's some missing energy, so he predicted that a neutrino would also come out, something that Fermi named neutrino, because in Italian you add an I-N-O, it makes it the diminutive. So a small neutron is a neutrino. Now, what Fermi tried to do, and all these people tried to do, you're scientists here, these scientists were very strange. They were trying to, to do God's work on a higher level. God created these, or the Creator, created these elements. The largest of them in the natural environment is uranium. Now, I didn't want to fly with a really huge bag, so I assumed there are 92 of the white ones and 146 of the black balls here. So this would be a very big bag, and that's the largest nucleus that exists in the natural environment. And what these scientists, these three groups in Rome, Berlin, and Paris tried to do is this. Smash a neutron into this largest possible nucleus, meaning the largest possible core of an atom, and see what happens. And what they really all believed would happen is that this would be absorbed. And, I can't do it because it's not possible. It is possible inside the nuclear reactor, but so this is what they thought would happen. And Enrico Fermi devised the whole theory in order to do this, and as you may know, he got a Nobel Prize for thinking that he did that, but he didn't. He didn't create what's called transuranic elements by something beyond uranium by absorption of a neutron. Now, he devised the whole theory to do that because natural radiation, alpha and beta, beta is an electron, and alpha is this. It's a nucleus of helium, so it has two white balls and two black ones, and this was the original idea, to try and enlarge it with natural radiation, alpha radiation. But it doesn't work, and the reason it doesn't work is the same reason, basically, that you only find one sock in your dryer. I always find one sock. The other one is gone because it's repelled. They have equal charge, so they repel each other. So this is what happens here. You have this nucleus, and it's positively charged because the protons are positively charged. And here comes this alpha particle, which is two protons and two neutral elements. So it's still +2. And it's like the two socks. They go in different directions, so you miss. But what Fermi discovered was if you do this, you wonder how somebody thinks that way. If you do this 100,000 times to beryllium, 1 in 100,000 times that you bombard beryllium with alpha rays, you get a neutron coming out. So it's a very inefficient process. 100,000 times you get one of these guys. Now, but this is kind of a silver bullet because it has no charge. It's neutral. So if it's aimed here at the nucleus, it's not going to be deflected by the opposite, by equal charges. So if it can go, it will hit. So he kept doing this experiment until he thought that he created something larger than uranium. But he didn't. At the same time, he let the other two groups in Berlin and in Paris know that he did it. And Irene Curie in Paris smashed something on the floor and screamed with being such jerks. He scooped us, but that's not what happened. So the third team in Berlin were cautious, Hahn and Meitner, and continued, yeah. Yeah, that's for 238. Yeah, but not the, you're right, but not in the process he was doing it, in the nuclear reactor. Okay, it didn't happen in his experiment. Yeah, of course, 239 is plutonium. But in his experiments, that's not what happened. He thought it did. There are obviously transuranic elements there where you go far beyond, you know. Plutonium is the first one, and there are several others. But that's not what happened in his lab, is what I'm saying. And he got the Nobel Prize for that, but it didn't happen. So, yeah. Well, he added something into it. A neutron will decay. A neutron will decay into a proton. And in fact, in the air, a neutron will decay in within 10 to 15 minutes. The half-life is about 10 minutes. Yeah. So he was expecting something larger, at least in weight or in number too, in atomic number, if once it releases, once it undergoes beta decay. So, and the quark changes. So that's not what happened in his experiment. At any rate, it didn't happen in any of these experiments. What happened was something totally different. So transuranic elements do exist. The periodic table goes far beyond uranium. But many of them are unstable, and others, such as plutonium, are created in different process, not in the kind of process that Fermi was working in his lab, or the other two teams. At least nothing was found. If plutonium was created there in small amounts, it was not found. It wasn't verified. I should be careful with that. It wasn't verified that it did occur. It does occur in nature, but it is not confirmed to have occurred. At any rate, 1938, Hitler took over Austria, and Lisa Meitner became stateless because she was Jewish. She lost her citizenship, and she had to leave her Berlin lab. She left in the dead of night and went across the Dutch border and then ended up in Sweden, of all places. So she was in the right place where people are getting Nobel Prizes, but she antagonized somebody there, a person by the name of Sieg Bahn, in whose lab she worked. Because she was stateless, she was a very important scientist, a prominent scientist by that time, and acted like one. And the head of the lab didn't like her, and he was very strongly connected with the Nobel Committee in Sweden. At any rate, in 1938, as a stateless person, a refugee with no money and no clothing, it was cold in the winter, and she had no warm clothes. She was visiting friends in the Swedish countryside, and her nephew, Otto Frisch, who was also a physicist, came to visit her. He was working with Bohr in Copenhagen. He came to visit her, and they were walking in the woods. He was on skis, and she was running next to him. She was 60 years old. She had just turned 60, and she could keep up with him running as he was skiing along. And she got a letter from Hahn in Berlin. Hahn took over their lab and wrote her a letter saying, look, what we find is barium. I don't understand it. In the solution, we find barium. Now, they were using barium chemically. He was an excellent chemist, and there was more barium there. So Lisa Meitner, on Christmas Day, 1938, sat on a log and started thinking, and she realized what really does happen in this particular process, which is fission. Rather than going larger, you go smaller. So when this happens, when a neutron hits a uranium nucleus in this particular kind of way, it splits in two, and barium is one of the products. Frisch went back to the lab in Copenhagen and told Bohr about it. Bohr was about to leave for the United States. He was about to take his ship. And he asked him, did you publish your results? And he said, no, we just came up with the idea. And he said, publish it right away. He came to New York, and Enrico Fermi, by that time, was at Columbia University. The reason was that his wife was Jewish, and he didn't like fascism, even though Mussolini gave him a title of His Excellency, and he was a member of his Academy of Sciences. But the family decided to flee. They kept their apartment. They let somebody into their apartment to turn on and off lights regularly so that people would think they were still there. And they left for Stockholm, where he was to receive the Nobel Prize for work on uranium. From Stockholm, they took a ship to the United States and settled first in New York at Columbia University and later to Chicago. So Bohr arrived in New York, and at the same time, Szilard, who was a Hungarian physicist who also moved to the United States, came to and worked with them, and John Archibald Wheeler of Princeton. So the four of them met at Columbia University and heard the news from Bohr, who had just arrived on the ship, that there is something called fission, where if a neutron hits a nucleus of uranium, it splits in half. The four of them theoretically derived the next idea in this process. So if this breaks, the question is, do you only get two smaller nuclei, or do you get something else? So if this splits, there'll be two pieces, but there will also be at least two of these. And when the neutrons go out, eventually they can hit other nuclei. And the four of them realized that when this happens, you can have a chain reaction. You started with one neutron hitting a nucleus, it splits, and the energy is released, in the words of Albert Einstein. A very small amount of mass can turn into a pretty large amount of energy because it's E equals mc squared. So m is multiplied by the square of the speed of light, which is a huge number once it's squared. 300,000 kilometers per second squared if you're using KMS system. So at any rate, you've got these neutrons coming out. They can hit other nuclei. Those will split, and you have a huge amount of energy. And if it's done just right, this is what the theory predicted, you could have a nuclear explosion, or if it's a more controlled way, you would get a nuclear power plant where something generating, it's sort of simmering. The process of chain reaction releases energy, but in a more controlled way. So after that, Einstein wrote his famous letter to FDR saying the Nazis might follow this process and develop a doomsday weapon. We must do something to stop him. I have to say that in 1972, I was an undergrad at Berkeley, and we had the physics department had a famous guest come and give us a talk, and that was Werner Heisenberg, who was the Nazi scientist. He gave a brilliant talk about quantum mechanics, matrix mechanics, and told us that when he derived matrix mechanics, he didn't know how to multiply matrices, which everybody found stunning because, you know, it's a simple operation, multiplying matrices. And Heisenberg said he didn't know how to do that. Everybody was charmed by him. He was 71 years old, and he was very charming and looked very much alive. And nobody asked him what he did during the war. In 2002, exactly 30 years later, I was in New York with my book on quantum mechanics, Entanglement, and my publisher said, well, you wrote a book on quantum mechanics, I'll send you and your wife to see this play, Copenhagen. So we went to see it, and the play was about what Heisenberg did in the war. And I don't know if you've seen it, Michael Frayn play. There are different scenarios as to what happened in this meeting in Copenhagen in 1941. Nobody even knows the exact time, the date of the meeting. It was sometime in the early fall 1941, although it may have been in October. And the play has different scenarios as to what happened and the implication about what Heisenberg did during the war. After the war, there was a biography of his and the story of the atom bomb, the Nazi bomb, and that was written by a German writer by the name of Jung, which presented Heisenberg as this great humanist who he remained in Germany, but he had no intention of creating a bomb. He was a chief scientist there, but he had no intention of creating a bomb, is what the book said. Heisenberg wrote a letter expanding on that, and Bohr in Copenhagen read it. He got very angry, and he wrote 10 letters to Heisenberg saying that's not what happened. But the letters were not released. They're supposed to be released in 2012. After the play, there was a lot of interest in the public and a lot of pressure on the Niels Bohr archive in Copenhagen to release these letters because people wanted to know what really happened in 1941 when Heisenberg, the head of the German atom bomb project, came to Copenhagen to meet him. And I saw the letters, and there in the book I reprint 2 of them. And the letters present a scenario that was not even in anybody's imagination, Frayn's imagination, when he wrote the play. And that story, rather than Heisenberg coming to Copenhagen and asking Bohr to make a pact between scientists to convince their governments to give up the nuclear, the drive for nuclear weapons, according to Bohr, what happened was that Heisenberg came there and said, look, in so many words, I'm a top theoretical physicist. I know how to make an atom bomb. I've been working on it for 2 years. We're way ahead of you. Give up. So that didn't work. The Manhattan Project did go ahead, and Nazi Germany did not get a bomb, which is why we're all here, I think. At least I wouldn't be here. What happened was that the Nazis knew a lot of things. They knew how to make. They knew you could make a bomb from plutonium and from uranium-235. Those 2 methods. That, of course, there are 2 kinds of bombs. They knew how to separate isotopes, the 235 from the 238, which is what the Iranians are trying to do now, or doing for many years now. And they knew. The only thing they didn't know was the critical mass, how much you need in order to get a bomb and how to keep it separate from the 2 pieces so they don't go critical. So these are technical aspects that, and remember Hahn, really the Germans did develop the first nuclear ideas in Berlin. So Hahn remained there during the war, and he was a very brilliant chemist. And Heisenberg was probably one of the top theoretical physicists. So they had the infrastructure. They had incredible knowledge about the bomb, but they lacked funding. So they couldn't create something like the Manhattan Project, for which we're all thankful. And the reason was, in fact, well, there are several reasons, but one of them is that the Allies kept bombing their heavy water installations in Norway, and that's a story that a lot of people know. I don't know if you've seen, there's a great movie about it many years ago about how they bombed it. So that prevented them from having a moderator for the reactor to keep the reaction at a certain rate. Although there are other ways. You can use graphite, as we know, and there are other ways of controlling nuclear reactions. But the biggest reason was that Hitler changed his direction. And instead of funding this project, he changed the funding, diverted it to the Peenemünde project, which created the V1 and V2 rockets that rained terror in Britain. So many people died in England, and there was a lot of damage caused. But on the other hand, Hitler did not get a bomb. Now, the Manhattan Project went ahead. Enrico Fermi created the first chain reaction. So the theory was discovered by these 4 scientists meeting at Columbia. Enrico Fermi at the University of Chicago created the small nuclear reactor, as you may know, under the football field, and created the first chain reaction in 1942. From then on, the road to the Manhattan Project was wide open. There were technical details to be worked out, but this was a very large industrial, scientific, and military operation. You know, part of it was not far from here at Hanford, still being cleaned up. Part was in Tennessee, and several universities, such as the University of California, University of Chicago, and several other universities were involved. It was a huge project, and it was controlled from Los Alamos, of course. The scientists that worked on it had different points of view. I had a grant from the American Institute of Physics, AIP, to look at the archives, to work at in the archives, and I got to see many of the interviews by the top scientists who worked there, and their views were mixed. Some felt that Japan should be bombed, and some felt strongly that it shouldn't be bombed. Leo Szilard, the Hungarian physicist, who was one of the first, he actually took Szilard said that he had the idea for a chain reaction before he met these other three, and he actually took a patent on chain reaction in Britain. At any rate, he led a petition signed by 68 scientists opposing the use of the atomic bomb on Japan, and demanding that it be used instead on on a desert island in the Pacific, or even on a ship, even though it's a small target for a nuclear bomb, but just to show the Japanese what would happen. Now, there was a miscommunication. FDR had died just before Truman became president, and we still don't know whether he actually got the petition in his hands or not. I couldn't determine that, and I couldn't find that anybody else knew whether he did get it. At any rate, Truman went to Potsdam in Germany and issued that ultimatum to Japan to surrender unilaterally, completely, with no conditions whatsoever, and the emperor had to go. The emperor is still in Japan anyway, so we didn't achieve that. And the statement was that the alternative to Japan is utter and complete destruction. Now, the Japanese were trying to sue for peace, as I learned from my research, and there are secret documents. They're ultra top secret documents that are now declassified. They've been declassified only the last few years, and these are communications that had been intercepted between the Japanese government and their ambassador in Russia, trying to sue for peace through the Russian connection here. But the Russians betrayed them. The Russians had no interest in helping them. The Russians invaded Japan on August 8, 1945, just 2 days after Hiroshima and a day before the bombing of Nagasaki. But the United States government did know that the Japanese wanted to surrender. So whether those two bombs were necessary is really questionable. So I think I'll stop here and see if you have any questions. I find with this book that people's questions lead to the best kind of discussion. Yeah. No. Yeah, I wrote in the introduction and the acknowledgments, there are so many people involved in this, I had to make a conscious choice as to who to include and who not. And even major characters that I didn't choose to, are not in the book. In fact, somebody asked me, why is Einstein a secondary character here? Now, the reason I'd written 2 books about Einstein already, and even though he's a major scientist, he had nothing to do directly with the atom bomb project. Of course, his formula is what allows it to happen, and he did write the letter to FDR. So he's instrumental in that sense, but he never worked with uranium. But my apologies to these people, or to their memory. Yeah, any other questions? You have the second question? Yes. Uh-huh. Yeah, I know. They're not considered as possibilities for a nuclear bomb. The 2 possibilities that are used industrially and militarily, 235 and plutonium. And the system that's used is different, as you know. The plutonium is, this is a design by John von Neumann of using a spherical explosive that throws the plutonium inward, and that makes it go critical, and it explodes. The Trinity test was that kind of a bomb, and the Hiroshima bomb was uranium-235, the bullet type of thing, 2 pieces kept separately, and then you have a conventional explosive throwing one into the other. That's little boy, and the fat man was fat because it was a large explosive device that throws. The other one was long. It was a long bomb, but then it got shorter, so they called it Little Boy. The bombing of Nagasaki was a plutonium device too. Most countries that make nuclear bombs make plutonium bombs, and they make the plutonium in reactors in the process that you mentioned. Iran, for some reason, insists on making the uranium bomb, and what I find so strange is that you always read in newspapers, or you hear in the news, that Iran claims it's for peaceful purposes, while Western governments believe it's for nuclear weapons. Now, since you brought the idea of the two kinds of uranium, it's important to make a distinction here. Uranium-235 creates these neutrons and the chain reaction that is explosive. Uranium-238 sort of simmers slowly, creating energy and transferring it to plutonium and to other elements that come out, iodine and you know, all kinds of other elements that come out. That's why you get this waste, the nuclear waste, which all kinds of elements, including radon gas, comes out of a nuclear reactor as well. And that's a problem because you have to release the gas. So they need a good filtering system as well to prevent the other elements, radioactive elements, from coming out. So when you have a reactor for peaceful purposes of generating electricity, what you use is uranium-238, which is the common element. That's 99.3% of the uranium in the world is uranium-238. What's found in the ore, and 0.7% is uranium-235. So you enrich it a little bit, so you have about 2 or 3% of uranium-235 in a reactor. It's mostly uranium-238. That can be bought commercially. It's shipped by sea from one country to another, or by truck. You know, it's commercially available. It's enriched. It's uranium that's enriched very slightly. You put it in a reactor, you make it into those pellets and place it in the reactor, and it burns this fuel for years. Now, uranium-235 is only used for bombs. If you have a research reactor, or you have a reactor on board a ship or a submarine, it has more uranium-235, something like 20% or 15%, something more than a reactor. It works better. It's like your grades of fuel that you use in your car. If you use uranium-235 and you refine it for years, and then use it in a reactor to make electricity, I can't think of an example that anybody would do. So. The overkill is just incredible. Well, first of all, the resources you're spending to refine the uranium could generate electricity for years. So it's a lie, but for some reason it's a lie that's perpetuated in the media in the idea of fairness. Well, Iran says it's only for power generation. You don't generate power from such pure uranium-235. Any other questions? Yeah.
So we've seen here at Hanford a lot of illness that came in. A lot of people were very sick and they grew up in that area and things like that. Is there a difference now when they're going to use uranium and have reactors and build them for electricity, things like that? Is it different than when they built Hanford?
Yes, Hanford was built for military purposes. That's where you create the plutonium. So it was not for power generation. The original Hanford reactors. I don't know if there were or are any civilian nuclear reactors nearby. Probably not. It was a military complex, and they were rushing to create a bomb as quickly as they could, and worrying about waste was not high on their list. So that's why there's leakage, and I guess it goes into the aquifer too, and into the Columbia River, and all kinds of places. So this is the site of a Superfund, right? Trying to. I'm sorry. Right. Right. Mm. Is it the distance away from food sources like agriculture, or is it? Yeah. No. There. Oh. Mm. Yeah, that's too bad. So to answer your question, hopefully nuclear reactors now, they're more careful. Also, there's a difference, there's a difference between American-designed nuclear reactors and others. That's why 3 Mile Island was not as bad as it could have been, because there's a containment building on top of it. So if the reactor explodes, there's some kind of containment. In Chernobyl, in the Ukraine, there was no containment building at all. And once the reactor blew up, it burned. And there are pictures, you can see the whole thing is wide open, it burns, and the stuff goes into the sky and goes everywhere in the world, actually. And they had lots of cancer cases, but it was more contained than people thought it would be. So it varies by country. The Eastern Bloc countries have a lot of nuclear power still. In Ukraine, there's several reactors in the same place, and I think they're building them now. They're part of Europe, many of these countries, Poland and the Czech Republic, and all these other former Soviet satellite states are now part of Europe, and there's growth there. So the question is what's the extent of controls that are used? Some reactors are safer and others are not. France, for example, has had, I think they say 80%, but I think it's more like 90% because they export their nuclear power to other countries as well. And they don't admit to ever having had any problem. And you drive through France, you see reactors, nuclear reactors everywhere. So.
Kind of a follow-up question, but if you had Secretary of State Clinton hear about this, what would you suggest?
Well, the problem is that global warming is such a big issue, and nuclear reactors don't emit any carbon. So it's a good way to control global warming, and also the dependence on foreign oil. The answer, I think, would be that we need to make them even a lot safer, but that costs money as well. So it's something that needs to be taken care of, but I think the uranium does have a future, along with wind and hydro and solar. Let me get his question first. Yeah. That's a good way to the future. What happened in Chernobyl is actually they shut down the emergency system, and their alarms, and 3 o'clock in the morning or so said, let's play around and see what happens with doing some test. Right, so it burns, being carbon, right. Right, the sarcophagus is there are cracks in it, right? Yeah, yeah. All these neutrons making the material brittle. Yeah, yeah. I found different varying estimates. Some people whose reports I read said that the uranium is abundant, and others said that we have something like 30, 40 years. You're right. Well, it depends on how it's exploited, the extent of exploitation of uranium. And also remember, the French and the Brits have been very good, at least for a while, with reprocessing. I think that Suffield in Britain is still running. The French, what's it called, La Hague, near Cherbourg. The last I heard was closed, but I'm not sure whether it's temporarily or not. In fact, the Japanese were sending their fuel to France to be reprocessed there. Suffield has had a lot of problems in terms of release of radiation into the environment. In fact, there was a plutonium found in significant amounts in the area there. So the safety, those reactors that reprocess fuel are not very safe at all, because think about it, you need to break these pellets and get some of the radioactive material out and control the rest, so you can't just let it go out. And it does, in fact, the Irish Sea is full of all kinds of the last I heard, salmon, Scottish salmon was found to have radiation levels in it. It was technetium, which they say is not that bad. It's used in medicine, but I'd hate to eat a Scottish salmon that has radioactive elements that leaked out of Sellafield. So to answer your question, with a mix of careful reprocessing, and also don't forget, Australia has a lot of uranium. So those estimates about 20 years or so, the Australians right now are widely, increasing their exploitation of uranium. Many parts of Australia, especially in the north and other areas, there's tons of mining, and companies such as BHP Billiton are making a lot of money right now with uranium. The mine in Germany was the first one that was used. The uranium that went to Marie Curie's lab came from Joachimsthal mine in Germany, and they brought a ton of uranium ore to the center of Paris with tree branches and rocks in it. And Marie Curie refined 1 gram of uranium, radium out of it. I'm not sure what the French did to clean the center of Paris from this ton of uranium. So, so I think the answer of whether nuclear power can be supported for many years is a question of how you utilize the mines, how you search. It's like oil too. I mean, there's oil in Alaska that has been used for a long time. Does Prudhoe Bay have a lot more oil for the next? I remember when I lived in Alaska, there were estimates of 10 more years or so. It's continuing to. So you don't know with resources like that how much there really is of it in the ground, how much it can be exploited, and also like gold that has various levels of purity. My gut feeling is that there's a lot of uranium. And it can be, the problem of safety is much greater. And don't forget, Chernobyl put a stop to, somebody here said that the United States stopped making reactors, was it 73 or 73? So that's before 3 Mile Island, which was 79. Right, well. No, I haven't. No. Yeah. Wow. Unbelievable. Huh. Did they all die right away? No, they didn't die. They didn't? Yeah, they got bone marrow transplants and some. Yeah, I remember that. Good. Any other questions? Well, thank you very much. Thanks. Thank you.